The title of tonight's presentation is Pasture and Hay. We're going to be talking about soils, fertilizers, and lime. And of course, I'm Casey Matney. I'm with the Cooperative Extension Service, housed out of the Kenai district in Soldotna, and we are a branch of the University of Alaska Fairbanks. So some assumptions we need to make so that we can understand what we're starting out with. Our Alaska soils are relatively low in clay content. Our soils usually have a fair amount of ash, and all have quite a bit of silt and sand. Most of that sand fraction is usually fine sand. The ash usually appears in what people call clay, but it's usually the high ash content is what people are referring to as clay. So if you hear people talk about that, that's usually actually what they're seeing. And most of the soils we have in Alaska are not well developed, which means they haven't been sitting in one spot for a really long period of time. If you get to the lower 48, you might look at soils in Washington, Oregon, all the way down across the Midwest. Those soils have been sitting there for hundreds, if not thousands of years, and are deeply developed and have lots of organic matter. Up here in Alaska, we have quite a bit of glacial movement. We've had a lot of volcanic activity. We've had a lot of river movement. And so our soils are relatively young, which means they haven't developed a lot of the finer sediments, especially clay. And what does this mean for pH? Most of our soils are acidic. So they're going to be usually below a ranking score of 6 or less. And our soils in Alaska are also cold, which means is that if there is organic matter in our soil, that's not turning over rapidly. It's actually barely turning over each year and releasing some nitrogen and other nutrients into the soil. So there isn't as much activity going on during the growing season. And then, of course, from October into May, there's very little activity going on in the soil because most of the soils here that we have are frozen, with some of the exceptions being in the southeast. When we're thinking about overall nutrients in the soil in Alaska, the nitrogen, phosphorus, and potassium levels are relatively low when we compare to regions of the United States. So those are also low. And then lastly, all of the soils, when we look at a broad spectrum of the whole state, going from very far north to very far south to the center of the state, those soils are very, very different. If you're on a valley floor, it's going to be much different than if you're on a ridge. And that's also going to be different if you're on a side hill or on the side of a slope. So all of our soils vary, but for most of what I just talked about, those are some common assumptions you can make for Alaska soils. So some of the questions you might have when managing your soil here in Alaska for pasture and hay is if you've taken a soil test, is you don't necessarily understand everything that's in there. A lot of the numbers come back. They're either going to be in percents, pounds per acre, or in parts per million. And how do I make sense of this in terms of what kind of fertilizers I need, in terms of how much lime I might need to add, and what kind of production I could expect from my land. So we're going to cover a lot of those aspects tonight. And so our goal today is to take you from maybe not understanding everything that you could see in a soil test, or you could see on the actual pasture just by looking at it, and coming up with some answers and some know-how about how we can manage it, and then also how can we look at what we've got to understand what's there so that we can make the most of it. So before we get into the soil test, we're going to do a quick review about soil sampling. We've done this in our earlier soil test and interpretation class that we did a couple weeks ago. We're going to go over some of the same basics again. And so it may be a review for some of you, but if not, here it is. So for fields and pastures, what we're going to be doing is taking samples spread across an area. So if we have a 100-acre pasture, we're probably divide that pasture into a few different types of management units that may be different on elevation, or they've got some different wetland stuff going on, or they've got different types of vegetation. We'll divide it up into some rectangles of interest that we want to know what's going on in the soil there. And when we do that, within the area that we're concerned about, we're going to take about 13 samples. We're going to take those 13 samples and we're going to place them randomly within family, or you just kind of spread it apart like you can see here in this diagram, so that there's some samples getting taken from everywhere to make one big sample. And when we look at our land, if it's got some slope to it, what we're going to do is we're going to try and divide it by the contours of the land. So if it's elevationally different, we're going to put samples on the top edge, or we're going to put samples towards the bottom edge. So if we were thinking 13 samples before, we could divide it into 6 samples on an above elevation gradient, and then we could step down a ways and then take 6 more samples at a lower elevation. So we have a general idea going across the slope what that soil is doing. And when we're taking our sample, a lot of times people will talk about taking samples down to 6 or 8 inches for a field or an area, but that's usually what you would do for an area that you're planting for the first time. Okay, if it's a pasture that you've long been managing, we're usually just going to take a soil sample from the mineral soil in the top 3 to 4 inches. So if you look at this little picture we have on the left side here, you can see there's a fair amount of litter from grass that's grown up. And then you can also see a little bit of shrubs trying to grow up through there as well. Well, we're going to go right below that grass, get to where it's actual soil. And then from that point, we're going to go down 3 or 4 inches to take our sample. And again, we're going to do that about 13 times in an area to get a general idea to get enough soil to send off to a lab. And when we're doing that, we're also thinking about all of the other areas within our pasture. Have they had different types of fertilizer or lime applications? Do they have different types of animal use, etc.? And we're going to divide that up and try and do multiple samples from each area. Maybe send in 3 or 4 samples from my property so that we have a good idea of what's going on. And for each of those samples you send to the lab, so if I've chosen an area, I've got a rectangle, I've done my 13 samples, those 13 samples have to be put into a bucket, mixed up all together, and then I want to be able to take back out of there at least 2 cups worth of soil and put it in a Ziploc bag to send to the lab. If the soil that you take, like if I was to go out and do it now because we've got a lot of snow melting, it's going to be very wet. And so what I would do is I would take those soil samples and I would either put it inside a paper bag and just kind of slush it out into a paper bag onto maybe an old work towel or something like that, or I would stick it on a surface that could easily drain and let it sit out a night or 2 so that it will dry out before I send it to the lab, so that they're not just ending up with a bag of goo when it gets there, because they're going to want that soil dry when it arrives. Okay, so let's talk about what we would want to do for just grabbing soil from our land and sending it off to a lab. When you do send it off, there's many different labs in the U.S. to choose from. We no longer have a state certified and state run soil testing laboratory. So the extension does have a worksheet for you. It's called Factors to Consider in Selecting a Soil Testing Laboratory. We've got a few example labs that we commonly use here in Alaska. That's just an example of some that are available, so you can choose any one you want. Again, that's publication FGV 45. And then most of the people, when they do select a lab, they're going to usually in a box that ends up being the least expensive way to do that. And if you're wondering how much do soil tests cost, the average range is from about $19 to about $30. It just depends on the lab you're sending it to and the type of process that they're going to take when they get it. And so when we send that off to the lab and we get back some results, we need to understand a little bit about how the plants use that nutrition that's in the soil. So before we start talking about some of just the tests themselves, we're going to talk about what the plants need. So when our plants are growing out on the pasture, or whether they're growing in a hay field, and it could be even a forage crop, maybe we're growing barley or something like that, our roots of our plants are growing down into the soil. And there's 3 ways that those roots come into contact with nutrients, which are minerals in the soil that the plants can use. The first one that the plants do is called root interception. So as the roots grow down into the soil, they're encountering new areas of soil. They're growing new root hairs as that root expands, and they're they're basically colonizing new areas of soil that have untouched and pristine nutrients there. So that's one of the ways, is through root interception, is that new growth. The other way is that our plants are pulling up nutrients is through mass flow. So if our soils are really wet, like they are now with all that snow melt, as the snow melts, it moves down into the soil, and it's still moving by gravity, usually left or right, and moving down slope to some other area before it kind of equals out. Well, as that water moves to the soil, it's also moving past plant roots. And while it does that, it's carrying nutrients with it, which are these ions the plant can use. And so that type of movement into the plant is called mass flow. There's one other type of movement, and this usually happens when there is no more really water movement going left or right or down slope. Everything's just kind of sitting static where it's at. And as the nutrients get used up by the plant root, it moves from areas of high concentration to areas of low concentration by diffusion to the root. So if the root is taking out ions, eventually it's going to try and reach an equilibrium in the soil water, and that's also another way the plants can get new ions or new nutrients for growth. So those are the three ways the plants are getting nutrients, and they're all out there in the soil, and they're all happening at the same time. So now that we know how plants might use those nutrients and how they're getting it, okay, it has to have water in the soil, and the plant roots are already there. But now once it's got a chance to get into the plant, now we can go back and look at the soil sample to determine how much of what is in the soil so that we know how much the plants need. And when you send your sample off to a lab, what's going to happen is they're going to take a little tiny sample of it. They're going to do some procedures numbers so that you can interpret. So again, when we're talking about our soil sampling, where you take your soil sample matters. If you only took one sample and it was right under a cow patty, that's going to have a lot of nutrients in it, okay? If I take one soil sample and it ends up happening to be over in a bare area ground where there was no plants at all, that's probably going to have a lot lower nutrients. So depending on what you're working with, where you take your soil samples, more than anything, will have a huge result on what you actually see on that test report. Okay, so when we get your test report back, the first thing that you're going to do is make sure you've got your name and location. It was written in the right place. So of course you sent it off to the lab correctly. And then also you have the location from where you took your sample. So if you had a hay pasture, you'd want to say, you know, it's from the northeast corner, or it was by the gate area, or maybe this was area, or maybe this was whatever you need to write down so that you know where it was located when you took that sample. The other thing you're going to do is if you've got any other indications, maybe the soil depth or something like that, you can also write those on there. A lot of folks will just take one sample and that's fine. But if you have multiple samples, you need to be really good at identifying those. So the first thing we're going to do when we look at our sample is look at pH. The next thing we're going to look at is cation exchange capacity. Then we're going to look at base saturation, and then phosphorus and nitrogen. These are some of the main important things we're going to do. So let's look at pH. If we don't look at anything else and we look at pH, the level of pH in our soil is huge. It helps determine whether or not nutrients are actually going to be able to get into the plant. So when we actually have a measurement on our soil test and it says, like for example on this one, that the pH is 5.2, it tells us our soil is acidic, because anything below a 7 is considered acidic, 7 is considered neutral, and anything above a 7 is considered alkaline. So we're trying to usually end up with a soil pH somewhere near 6.5, but you can see here that we are not at that. We have a 5.2. And where it says water on there on the left, it says H2O 1:1. That means our soil sample was mixed 1:1 with water and just measured for pH. Nothing was done to it. Okay, the score right above it where it says buffer score, that score is actually where we took some soil from our property and then they mixed it with lime reagent to determine how much the soil actually changed when we added that reagent to it. And you can see here it went from 5.2 to 6.6, which tells us it changed quite a bit. And that index, that relative difference between the true pH and how much it changed in reaction to that reagent, will tell us how much lime we need to apply to get the NPH that we want. So here's a little quiz question for you. If we're thinking about most of our pastures and hayland that's out there trying to grow grasses or forage, which is the better pH? Is it A, 4 to 5.7, B, 5.7 to 7, C, 7 to 8, D, 6 to 7.5, or E, above 8 for pH? Well, hopefully you guys chose B. Most of our grasses are tolerant of pH of 5.7 to 7, and that is also a very good range of pH where most of the nutrients are available to our plants. Why does this matter? If we look at this chart here, the yellow area is that zone of 5.7 to 7, and in that zone you can see that a lot of the nitrogen, the phosphorus, and potassium, and calcium, and magnesium, which are all considered major nutrients that the plants need, are quite available. As you go further to the left, higher, which is lower in acidity, you're going to see that all of those numbers start to diminish quite rapidly. And if you go to the right, above 7, you can see that while we retain a lot of those nutrients, some of those micronutrients down below, like iron, manganese, boron, copper, and zinc, and molybdenum, also change a little bit. That pink zone, that kind of pinkish orange salmon color at 6.5 on either side, is kind of an ideal zone of pH where we really want to keep our pH at for our plants. So ideally we would have it in that zone. But again, we just want to make sure we're getting it above 5.7. So let's assume that you guys have taken a sample and it came back with a score of 5.4. In terms of how much lime we need to add, that doesn't tell us anything yet. We actually need that buffer score. Okay, that buffer score will tell us how much the soil is likely to change with the addition of lime. So if we look at this chart shows us a buffer score on the left and the tons of lime to apply in the middle column, or the pounds of lime per 100 square feet that we need to apply for a given area. So if we have a buffer score on the left and tons of lime needed in the middle column, what's it going to be for different levels? So if we choose our sample and ends up having a buffer score of 5.7, that means we're going to need to add about 4.6 tons, which is over 9,000 pounds of lime per acre to bring our soil pH to near 6.5. And if you're having to buy this lime, which most of us would, this would be quite expensive, okay? If we actually got our soil sample back, instead of having that buffer score that was 5.7, it had a buffer score of 6.4, that would tell us that we need to use less than half the lime we did at 5.7, and we actually only need 1.9 pounds, or 1.9 tons of lime per acre. A huge difference in the amount of lime needed, and also a huge difference in the amount of money needed to be spent on lime to raise the soil pH. If we're going to have proper pH, that's great, because that's going to give us all the opportunity to grow different types of plants for forage. And so we have many different plant species options. If we were below pH of about 5.7, one of the few grass species we could grow would be Timothy. It has a fairly low pH tolerance, so it can grow at lower pHs. However, if we wanted to grow things like brome, it needs to get above 5.7. So, having a better pH will allow us to grow different types of plants. If we have pH that is near 6.5, that means that it's going to have a better ability to get nutrients into the plant. And if all of those things are equal and we've got a good level of pH, like the microbes, the bacteria, and the fungi in the soil are going to be a lot more healthy too, because all of those nutrients are going to be available to them, and the growing environment for them will be a lot more hospitable. So lime, we were talking about lime to change our pH. Lime's needed to raise the pH from acidic soil to bring it more near neutral. There's different types of lime. For the most part, when we're talking about hayland and pastures, we're going to be using powdered lime. And powdered lime is really just pulverized limestone or chalk. Okay, it's mostly calcium carbonate. It's usually going to be above 90%, usually above 95% calcium carbonate. There are different types of lime out there. The main two differences are they're usually just regular agricultural that has calcium carbonate in it as the main constituent. The other type of lime is dolomitic lime, and that has magnesium in it at a level of about 10%. So if your soils from your soil test came back and they're like, yes, we need to raise their soil pH, but it's also quite low in magnesium, then I would choose dolomitic lime for a percentage of the lime that apply to my pasture, because that will also raise my magnesium while also raising pH. So it just makes it convenient for adding magnesium while changing pH. Lime in general can be expensive. So if you find out that you need to add like 5,000 or 9,000 pounds of lime to your property, you may not be able to do it all. And so if you want, you could cut back on that, but by the amount that you don't apply, it will reduce the effect proportionately. So if you knew you needed to apply 6 tons of lime and you only applied 3 tons of lime, it's only going to get you about halfway toward that. And you apply 6 tons, get 6.5. That you're probably just going to get about 6.1. So if I only apply half of the rate. And of course, you are the one who decides how much lime to apply, because usually it's an economic question, and it also depends on the types of plants that you're growing for your forage. When we're thinking about when we do our lime, it's usually best done in fall, or if this is your first planting, right at the time of tillage or disking, when you're going to start planting. Mixing that into the soil as best as possible, getting more water into the soil with that lime, and letting it sit for a while before your plants are growing. That reaction time in the soil is key to having it change the soil pH for the plants start growing. And of course, if you're going to apply a lime, especially since we're adding powdered lime for most of our rangelands out there to change the pH, you're going to avoid windy days, because that's just going to blow your lime everywhere and you're going to get poor distribution across the landscape. So what else do we need to know besides pH? We just talked about lime, talked about how we understand the soil test, but there's more to know in the soil report, because we're going to want to know how to change things to make things better using fertilizer. And the next thing to know besides pH to understand fertilizers is the cation exchange capacity. Cation exchange capacity is just a number on the soil report, right, when you look at it, but it actually tells you how many parking spots are in your soil to hold nutrients. The cation exchange capacity is usually the number of charged ions, cations, that the soil can hold. So when we're thinking about those cations, right, if I've got a cation exchange capacity like I have here, 4.69, relatively that I've got that can hold nutrients in the soil. If that number was 15, the amount of parking spots in my soil would have been tripled, okay? So it's a relative number of the amount of area that the nutrients can park or sit in your soil and be available. If you have a cation exchange capacity below 10, that usually means that you have a mostly sandy soil. Okay, it also means it's usually fairly low in organic matter. If I've got a cation exchange capacity of between 10 to 20, it's usually telling me I've got a medium textured soil with a fair amount of silt in it, and I may have a fair amount of organic matter in it. Once I start to get into soils that have above 20 for cation exchange capacity, it has a lot of ability to hold nutrients, but it's also telling me the soil texture is quite fine. Maybe it's a very fine silt or closer to a clay, and it's probably also got a lot of organic matter in it. If you start to see very, very high cation exchange capacities, you're usually ending up with kind of a mucky peat type of soil when you start to see your cation exchange capacity get into the 30s and 40s. And let's talk about organic matter. Organic matter is in the soil. It's usually coming from decomposed plant matter, and that decomposed plant matter is actually determined by the amount of material that's burned off at 360 degrees Celsius when you send your soil sample off to the lab. So they're going to take your soil sample, weigh it, and it'll be already dried, and then they're going to heat it up to 360 degrees Celsius, and whatever burns off is going to be considered organic matter. For a lot of our Alaska soils, it might not be very high in organic matter, so it might be like anywhere from 7 to 11 or 12 organic matter. If we're looking at some of the areas that have a lot of peat in it, it might be upwards of 30 or 40% organic matter. Okay, it could be very high. But that's how they do it, and that's what they're looking for in your soil when they heat it up. When we look at the amount of organic matter that's in the soil, why does it matter? When we have above 20% organic matter in our soil, it's no longer a mineral soil, which is the conventional way of looking at soil as a mineral soil. But once we get above 20%, it's no longer considered mineral soil. It's actually an organic soil, which means it changes the ideal pH. So instead of being 6.5 for ideal pH, the ideal pH is anywhere between 5.8 to 6.5. So you can get away with having a lower pH. Okay, so if I have a pasture, it's high in organic matter, the pH is only at 5.7, 5.8, 5.9, I'm probably not going to add lime because it doesn't need it because it's organic soil. That organic matter changes the way nutrients are released to the plants, and it changes the way the soil can hold on to nutrients. So it changes everything in terms of pH in lime. Okay, and again, just the general zone that we're looking for, okay, for our soils, especially organic soils, is anywhere from that 5.8 to 6.5. That's great. And if we can get into that zone and not require lime by having high organic soils, that's great. Going on to nitrogen. If we have nitrogen in the soil that's going to be released, okay, that would be from decomposing organic matter. Okay, so that number is arrived at by looking at organic matter. In Alaska, most of our soils are frozen at some degree from October almost into May. So nothing is happening and nothing's getting broken down. Okay, once it gets into the latter part of May, June, July, August, September, okay, stuff is happening in the soil. The soil is probably getting up to near 60, if not just above. And there's some organic matter being released, decomposing and releasing some nitrogen in the soil. This number you get back on your soil test really doesn't mean a lot because it's probably only about actually 10% of what it really is saying. So if it says 114, there's actually probably only about 10 pounds of nitrogen being released into our soil, which is very low and almost non-existent. So we don't usually use this number for our interpretations. So when you see this here, don't think of it in terms of the amount of nitrogen your soil has. Just know that you've got organic matter. Eventually, over time, it will slowly release some of this nitrogen, but it's not enough to give us what we need for our plants. Okay, all of the other measurements that come out from our soil for phosphorus and everything else is going to be using the MELIC3 method. That's a method that's really good for us in Alaska because it's good for soils that are high in acidity, have the organic matter and the temperatures that we have during our growing season. So this extraction method that they use in the lab, the MELIC3 method, is the one you want to use when you send off your soil sample. They usually give you an option and just make sure that you choose it. Okay, so what do we get back when we do the MELIC3? A bunch of numbers, and we're going to be going over all these numbers here on the left. So let's go first with the big three, which is nitrogen, phosphorus, and potassium, which here we have represented with N, P, and K. Okay, so first one that you're going to see on this one is phosphorus. The yellow zone there is when it came back from the lab. It said it had 101 when it was in term of P2O5, okay, which is potassium pentoxide. But when we look at it as parts per million of just plain phosphorus, okay, it's at 22 parts per million. The ideal zone that we want to see for just about any type of plant growth would be above 100 to 170 parts per million. So this is the kind of number we would normally see on land that has been newly cleared. Same goes for the potassium number. It's at 28 parts per million, and we'd like to see it much higher than that. So this is very low for that as well. And then nitrogen down at the bottom. We combine both the nitrate nitrogen and the ammonium nitrogen. Those numbers are very low here. They're not even to 4. So it tells us there's almost nothing in the soil to support plant growth, okay? When we look at the other nutrients that are out there, things like sulfur and calcium and magnesium, this is where they're located. So sulfur up there at the top, it has 18 parts per million, which isn't too bad. Calcium is very important for plant growth. In Alaska, we usually have an abundance of calcium. So anything above 250 is usually okay. Magnesium, we want it to be fairly high, closer to 100. Above 150 would be excellent. Here it's quite low, so this is a soil where we want to add some magnesium. Sodium doesn't matter so much for most of our land when we're doing hay production or in pastures. However, it's always good to look at if it gets starting above 100 parts per million. Usually we have a problem. If you're using a lot of fertilizer and maybe too much, sometimes this number can go up. And then boron. Boron is something that it's overlooked a lot. We want to make sure that boron gets above 1 part per million. Right now, it's very deficient in the soil on this sample. It's below 0.2. So boron's something that's needed as a micronutrient for plant growth. And so we might consider adding boron to our pasture here. Other micronutrients that we're looking at, we're going to go to those. So looking here, we've got iron, manganese, copper, zinc, and aluminum. The iron, manganese, copper, zinc, and aluminum, I will tell you, for the most part, on most of the land we have in Alaska, are usually okay. It's very seldom that we start to see this being a problem, especially for areas that are going to be pasture or for hay. So these numbers, you could get away with not looking at sometimes, but it's always good to look at. If for some reason that was 0.5 or below for any of those numbers, we'd have a huge issue. So those are the general types of ranges we want them to be above. Let's talk about base saturation. I know we're going through this quite quickly, but for most of our hay production and pasture land, we can get away with knowing just a little bit about these things. But base saturation is relative to some of the numbers we were already talking about. So let's talk about that again. So base saturation is a relative amount of cations in our soil as belongs to the cation exchange capacity. So what's that mean? So if we go in here and we start looking at numbers, the calcium, magnesium, potassium, and sodium percentages along with hydrogen are all relative to a 100% level of cation exchange capacity. So if I think of my bank account as being 100% cation exchange capacity, when I add up all of these numbers, okay, that's what we got. Of that bank account, 41% is calcium here in this example. 8%, which is almost 9%, is magnesium. Potassium is about 1.5. Sodium is at 2.6. And then other bases around 7. But our hydrogen levels are about 39. Hydrogen here might sound a little bit benign, but actually hydrogen is a bad number when we're thinking about nutrients in our soil. Because our soil sample has low pH, that has made a lot of hydrogen available in the soil. And because of that, it's taking up space in our cation exchange capacity, which is taking up parking spots that we could be using for nutrients. So that's why we start talking about things in terms of parking spots. So we want to move all of those hydrogen out of those parking spots and open it up and displace it with calcium, magnesium, more potassium. So how do we do that? We raise the pH. If we raise the pH, the hydrogen level goes away. If you get your soil pH somewhere around 6.5, your hydrogen level will usually be below 10%, which opens up about 30% more of those parking spots on our cation exchange capacity, which is the parking spots for nutrients in our soil. So what numbers do we want to see? Well, if you've added fertilizer to get to the part per million levels I was talking about earlier, that zone of calcium percentage should end up being between 60 to 80%. So let's say we've added lime and added nothing else to the soil. That should get rid of the hydrogen and bump up the calcium percentages to between 60 to 80%. For magnesium, it should do the exact same thing. Should bring it up somewhere between 10 to 20%. And if we go down to potassium, it should also do the same thing and hopefully get us near 5%, okay? The sodium level will also increase. That's not something we're super proud of, that we don't want to have a lot more of. So obviously we'll avoid doing anything that adds sodium to our soil. And for the most part, when we're doing hay and pasture production, this is not a huge issue for us. So we've looked at our soil samples and we've looked at some of the numbers. We kind of know what's high, we kind of know what's low, and we do know what our soil pH is and if we need to add lime or if we should. Okay, so that's where we're at this point. When we have our soil tests, remember they're just a point in time measurement. So you took it at one point in time, like say last year or this year, and then maybe since then you've grown other crops, or maybe you've taken more harvesting. Maybe you've had some animals in that area they've dropped a lot of dung and urine out there. It's changed things. You know, things change over time. So what we need to do for hay and pasture production, ruling out all those other things, is we know we're going to pull probably off about 4,000 pounds of dry matter. Hopefully that's about 2 tons of forage off of our property per acre per year. And because of that, we know we're going to be doing that. We usually want to fertilize so that we're maximizing our plant production to pull off that amount. So what does that end up in terms of fertilizer? We're going to be talking about that. We're going to be talking about that in detail for different areas in Alaska. Taken across our pastures and our hay fields is going to be ideal. Okay, so let's move on. So fertilizers, this is the main thing that people want to know about. I will tell you that most of the fertilizers that people will use are going to be conventional. Some folks want to use some type of organic method, and that's usually just not feasible at the scale when we get to larger properties. You can do it, and if you've got lots of compost available or manure available, you can get it done, but it's going to be a little bit more labor intensive, and you're going to have to find a source that's going to be able to provide all that material for you. So conventional fertilizers on average are going to be less expensive. They're going to be easier to apply and more available. And they really do work quite well. And we're going to go over all the different prescriptions that's needed for the South Central, for Kenai, and then also for the interior. And remember, when we're talking about fertilizer, we're thinking about how much fertilizer we need to apply to the landscape so that we're going to maximize our production at least around 2 tons per acre of dry matter. So when we think about fertilizer, all of us have heard of the 3 numbers on a fertilizer bag before. Some of us will get super sacks or we'll get individual sacks of fertilizer, and we might be mixing with other types of bags of fertilizer, but you need to know what's in the bag. So in this example, this is just a very generic fertilizer bag. It says 21-3-20. That means it's 21% nitrogen, 3% phosphorus, and 20% potassium by weight. So it's percentage of that 50 pounds right there divided among those 3 different nutrients. So when we add 21 plus 3 plus 20, okay, that's going to actually give us 44% fertilizer in this bag. The rest of that 56% in that bag is inert material, just going to be inert material, usually some mineral rock inert component, and it's not going to be providing anything to our soil, okay? So that other percent, that 44%, is the actual active nutrient ingredient that will end up on our landscape. And that 21% nitrogen out of that 50-pound bag is actually only 10.5 pounds of nitrogen. That 3% of phosphorus in that 50-pound bag is only 1.5 pounds of phosphorus. And that 20% of potassium comes out to be about 10 pounds of potassium in that 50-pound bag. So out of all of that, you're only ending up with about 22 pounds of fertilizer, okay? So out of a 50-pound bag is 22 pounds of fertilizer. So now that we've got that talked about, we can move on and start talking about more in-depth things, okay? Conventional fertilizers, when we think about it, they're all going to be listed as N, P, and K. But there are 3 other main ingredients that we want to know, because these are usually tied into the mix of what's in the fertilizer, and that's sulfur, calcium, and magnesium. And so here I've listed out all of the main conventional fertilizers that might be used or available to buy, okay? So we have urea, ammonium nitrate sulfate, ammonium sulfate, ammonium phosphate sulfate, calcium nitrate, monoammonium phosphate, diammonium phosphate, triple superphosphate, single superphosphate, potassium nitrate, sulfur-coated urea, calcium sulfate, or gypsum, potassium magnesium sulfate. So all of these things can be bought. They're all available. And those are just a lot of the conventional fertilizers that are out there. In terms of just nitrogen, things that we're looking for are high in nitrogen. I've got those ranked here in order of having the most nitrogen. So urea is going to be your best, cheapest source of nitrogen, followed by ammonium nitrate. sulfur-coated urea, ammonium nitrate sulfate, ammonium sulfate, diammonium phosphate, ammonium phosphate sulfate, calcium nitrate, potassium nitrate, and monoammonium phosphate. Okay, those are all sources of nitrogen. In terms of phosphorus, we've got triple superphosphate, single superphosphate, monoammonium phosphate, diammonium phosphate, and ammonium phosphate sulfate. Notice that phosphate is a key part of all of those words. And then we have potassium sources, and we've got four main ones here: potassium chloride, potassium sulfate, potassium nitrate, and potassium magnesium sulfate. Okay, so what does all of this mean? Well, now we're going to try and put things together in rates. Okay, each one of those different types of conventional fertilizers has a different percentage. So if I go back up and I look again at conventional potassium here, potassium chloride had 0, 0, 60, 0, 0, 0, which is NPK for those three numbers in the parentheses. So it has 0 nitrogen, 0 phosphorus, and 60% by weight of potassium. With that knowledge and knowing what's in the meaning behind all of those numbers, we're going to look at those rates. So again, we're going to first go over South Central, then Interior, and all of these numbers are coming out from the Field Crop Fertilizer Recommendations for Alaska Forage Crops, and that's our publication FGV 149A. So let's take a look at Timothy. All of these that we're going to be talking about now are specific to different types of varieties of forage. So for Timothy in South Central, we're going to be wanting to add 60 pounds of nitrogen, 20 pounds of phosphorus, 25 pounds of potassium, and 32 pounds of sulfur. This is on a per acre basis. So these numbers are in pounds. When we're looking at fertilizer bags, those other types of numbers we're looking at were percentages of nutrient by weight. But right now for this prescription, we're looking at pounds of fertilizer needed per acre. Okay, and if we look at newly cleared land that's going to be planted in Timothy, we'd want to increase the phosphorus rate by 50%. So in order to do that, we're going to increase the phosphorus level by 10 pounds of phosphorus. So for newly cleared land for Timothy, it's 60 pounds of nitrogen, 30 pounds of phosphorus, 25 pounds of potassium, and 32 pounds of sulfur. And I have a little footnote here. It just tells you that phosphorus pentoxide, which is that P2O5, contains 43.64% phosphorus. If you read your numbers and go back to what is listed in the publication I just mentioned, it talks about phosphorus in terms of the phosphorus pentoxide. And so what I've listed here in all of the slides we're going to be seeing tonight is just straight phosphorus. How many pounds of phosphorus needed? Because when you look at phosphorus as it's rated, when you buy it in the store, it's just pounds or percentages of phosphorus. So we're not going to worry about the P2O5 number in any of these numbers we're talking about tonight. We're also not worrying about any of the potassium oxide or the K2O. Okay, we're going to be just looking straight at pounds of phosphorus, pounds of potassium, so that you can relate that back to actual nutrients as percentage numbers in the amount that you can buy. So again, that was Timothy here for South Central. Moving on to smooth brome. This is for nitrogen, phosphorus, potassium, and sulfur. We would be wanting 80 pounds of nitrogen, 30 pounds of phosphorus, 100 pounds of potassium, and 32 pounds of sulfur. The main difference for newly cleared land is that it's going to be almost devoid of phosphorus. And so again, we raise that phosphorus level. So instead of being 30 pounds, like we've seen for the regular smooth brome prescription, we're going to raise that level to 45 pounds of phosphorus. Going down to blue joint, which is our Canada reedgrass, it's that common grass that we have on most of our rangelands here in Alaska. It's also quite invasive and comes back pretty strong to some of our pastures. Okay, we can increase the production on that forage, and it can be very good forage when harvested early. And so we're looking at 100 pounds of nitrogen per acre, 30 pounds of phosphorus, 50 pounds of potassium, and 0 sulfur needed. And if it's newly cleared land, and for whatever reason we've gone back in there and we've seeded it with Canada reedgrass, we want to increase it from 30 pounds of phosphorus to actually 45 pounds of phosphorus per acre. When we go to oats and barley in South Central, we're going to be looking at adding about 60 pounds of nitrogen, 35 pounds of phosphorus, 50 pounds of potassium, and 0 for sulfur. And again, we're just going to raise that level when we're looking at newly cleared land, and we're doing that for our phosphorus. And so instead of 35 pounds, it would be 55 pounds of phosphorus for newly cleared land per acre. Looking at rye, rye is going to have different levels of need depending on whether we're letting the rye go all the way to head, or we're just have rye that's in the vegetative stage and we're trying to increase leafy production. So if we're trying to increase head production and we need more nitrogen to do that, okay, we're going to use 100 pounds of nitrogen, 45 pounds of phosphorus, 50 pounds of potassium, and 0 sulfur in South Central per acre. If we're looking at the vegetative stage, it would be 30 pounds nitrogen, 30 pounds phosphorus, and 50 pounds potassium with 0 sulfur. And of course, for newly cleared land, we're just going to alter all of those numbers there because rye has to be reseeded each year. And we're going to increase the 45 pounds for the heading rye to 60. And for the vegetative rye, we're going to change that 30 pounds to 45 for phosphorus levels. Again, that's all pounds per acre. If we're looking at growing rape or turnip as a forage crop for fodder for animals, we're going to actually need a fair amount of nitrogen. So we're going to need 100 pounds of nitrogen, 25 pounds of phosphorus, 40 pounds of potassium, and 0 for sulfur. And again, if it's newly cleared land, we're just going to bump up that phosphorus level by 10 pounds. All right, moving on to the interior rates. So we just went through South Central rates for a lot of the common pasture and forage production that we have here. Let's go look at interior rates for smooth brome at the time of planting. So if this was a new planting, okay, of smooth brome, we would need 60 pounds of nitrogen, 25 pounds of phosphorus, 25 of potassium, and 10 for sulfur. If it's an established stand, we'll be using 60 pounds of nitrogen, 20 pounds of phosphorus, 15 pounds of potassium, and again 10 for sulfur. If it's after the first cutting, we're going to leave out phosphorus, potassium, and sulfur, and we're just going to come back in with about 60 pounds more of nitrogen. So that's if you've taken smooth brome, done a first cutting, and then come back in, and you're going to probably take another second cutting later in the late summer or early fall. You would add that 60 pounds of nitrogen. Again, if it's newly cleared land, it's never been put into anything before, you're going to take these smooth brome numbers and increase the phosphorus. And so we're going to increase it up to 30 pounds of phosphorus per acre. Moving on to Timothy. If we're looking at Timothy here, again, the nitrogen, phosphorus, potassium, and sulfur levels are going to be 80 pounds of nitrogen, 15 pounds of phosphorus, 15 pounds of potassium, and 10 pounds of sulfur. And again, if this was newly cleared land, we would increase that phosphorus rate by 10 pounds for Timothy. Moving on to bluegrass, our different species that we have. For planting, for a new planting, we'd have 60 pounds of nitrogen, 25 pounds of phosphorus, 25 pounds of potassium, and 10 pounds of sulfur. For an established stand, we're just going to reduce the phosphorus level by 5 pounds and reduce the potassium level by 10 pounds. And again, if we're going in after a first cutting, we're going to do the same thing as we did on the smooth brome and just come in with 60 pounds of nitrogen. Then for a newly cleared land, we're going to do like we did earlier and just raise the phosphorus level up to 30 pounds per acre. Going on to the next page. So if we have bluegrass pasture, and so we're not harvesting it for hay, we would just come in with 70 pounds of nitrogen, 15 pounds of phosphorus, 20 pounds of potassium, and 10 pounds of sulfur each year. So if it's a heavily used pasture, we want to do all of these things in the spring. And then of course, for seed production of bluegrass, so we're just trying to produce seed so that we can harvest it and sell seed, we're going to be looking at 100 pounds of nitrogen, 25 pounds of phosphorus, 50 pounds of potassium, and 20 pounds of sulfur. see there, seed production, we've increased the sulfur quite a bit there. Looking at our interior rates for oats, barley, and rye, if we have hay or silage production, the rate we're going to be looking at is 90 pounds of nitrogen, 20 pounds of phosphorus, 15 pounds of potassium, and 10 pounds of sulfur. And for newly cleared, we're just going to increase that phosphorus rate by 10 pounds. And for fodder, rape, or turnip, we're going to have a high level of nitrogen at 100 pounds per acre, 25 pounds per acre of phosphorus, 15 pounds per acre of potassium, and 10 pounds for sulfur. And of course, if it's newly cleared land, we're going to increase that phosphorus rate by 15 pounds. Okay, so those are all pounds of nutrient needed per acre. Okay, so what does this mean in terms of an all-around, I don't know what's in my pasture, I just live in this area and I want to apply fertilizer? Okay, some of the generic rates that are out there for Kenai Peninsula are 80 pounds of nitrogen, 40 pounds of phosphorus, 40 pounds of potassium, and 32 pounds of sulfur on a per acre basis. For South Central, that would be just around the Palmer, Matanuska, Point McKenzie type of area. It would be 140 pounds of nitrogen, 60 pounds of phosphorus, 120 pounds of potassium, and with no sulfur, and we would split the nitrogen. So we would go in early with nitrogen at 70 pounds, and midsummer, we would go in with another 70 pounds of nitrogen to keep it going. For the interior, just a generic rate would be 120 pounds of nitrogen, 40 pounds of phosphorus, 20 pounds of potassium, and 10 pounds of sulfur. And of course, at any point you could go and reduce these levels and rates because, you know, at these levels, it would be the absolute maximum amount of fertilizer you would want to apply. And if you came in with just a little bit, it would still improve production.